Hello, this is the Crystal Clear Electronics 7th chapter's first part, where we will learn more about switching devices. Before we get started, I'd like to make a short introduction about ourselves. I'm Henrietta Bankuti. I came to the world of electronics from IT. I was introduced to Crystal Clear about 4 years ago, and since then I have read every written material at least once. Unlike many of the other presenters, I didn't learn things at school but at home on my own. For example, I built an LED string light last Christmas based on the Crystal Clear tutorials, which showed me that it's not that complicated. You will find a download link in the video description that contains a list of all the components used in the Crystal Clear electronics tutorials. These can be ordered by anyone from various online electronics stores. We encourage everyone to get these gadgets and try to build the electronics while learning. Only then will the knowledge really sink in, and only then will you be able to cope with the later parts of the curriculum. Our presenter today is Zalán Gyuricza. Hello Zalán, can you say a few words about yourself?
Hi, I'm Zalán Gyuricza, a fourth-year electrical engineering student at BME. Besides the university, I'm working, where my job is also my hobby, programming microcontrollers for various tasks. What motivates me the most in my job is that I can create working, useful objects, and they help us in our everyday life. I think it's a very special feeling when you work on something for days or even months, and at the end of the project, that thing works. That's actually why I became an electrical engineer.
Thank you for the introduction, Zalán. Now let's get started. The 7th chapter was written by Dávid Kulcsár.
In your everyday life, you'll come across switching devices in many places. Perhaps the simplest example is the light switch that you can see on the table here, which is used to turn on and off the lights in the house. But it could also be as simple as the switch for the blender or the mixer in the kitchen.
But the microwave switch is not so simple, because you can set how long the microwave should be on.
Then we are talking about some kind of time switch, which is a bit more complicated. But there are more complicated functions, for example, when you turn on a computer. You press a button at first, and then millions or billions of switching devices make sure that your computer actually turns on, so you can watch this video, for example. But you probably don't know about these tiny switches because they're hidden inside your computer.
But now let's start at the beginning. Look at a simple example and let's blink an LED on the breadboard.
You can see the connection on the screen, and as it's very simple, we're going to put it together live. If you can, pause the video, find your breadboard and put it together with us. If you found your breadboard, then we can start putting together the wiring. Let's make the circuit together. First, we connect the DC terminal to the power rail of the breadboard, into which we will plug the power supply later. Then, we insert the current limiting resistor to prevent the LED from failing. Afterwards, we also put the LED in place, making sure that the shorter leg of the LED, i.e. the cathode, is connected to the resistor and through it to ground, or GND. The last step is to connect one end of the wire to the longer leg of the LED, the anode. Here, next to me, the connection will be made in a second. Henny, please connect the power supply to see what will happen. We can clearly see that the LED lights up. This happens because the circuit closes and the electricity flows through the LED. If you unplug that green wire, then the circuit will be broken and therefore no current will flow, and consequently the LED will not light up. So you can actually implement a switch by connecting or not connecting this wire to the breadboard.
Well, this way it's a bit too overcomplicated to make it, and it can be quite slow to perform this switching operation. It would be advisable to use some kind of switching device.
Yes, but there are many different types to choose from. There are mechanically controlled ones and electronically controlled ones. The mechanical ones can be further subdivided into bistable and monostable.
Or more simply, switches and push buttons.
That's right. And the electronically controllable ones include relays, bipolar transistors, MOSFETs, and optocouplers. Let's start with mechanical switching devices.
The point of these are that the state of the switch can be set manually according to whether we want to open or close the circuit.
The diagram on the left shows a general switch. On the right is a schematic diagram of the same switch. The numbers 1 and 3 mark the terminals of the switch device. These terminals can be inserted into our circuit to make our switch work. The terminal, in other words leg, marked with number 1 is called pole. This is the common output of the switch. This means the following: the output marked with number 1 is in contact with one of the outputs of number 3. The state of the switch is symbolized by the number 2 moving contact, so this can be set by tilting the switch. In case of switching devices, pole number gives the number of moving contacts, so how many subassemblies can be found inside the physical device which are capable for switching. Number of switches marked with number 3 defines how many terminals our pole can connect to. So this is the number of contacts for a single pole. In this picture, you can see a mechanical tilt switch in assembled and disassembled states. This switch contains 2 switching subassemblies. The switch is realized by a moving switch. When the switch is tilted, the spring mechanism, in the photo it's green, built into its cover, creates a force in the direction of the moving switch, which tilts the moving switch in the direction of the contactor, so it connects to the pole and the contactor. If the switch is tilted to the other direction, then the moving contact will move to the other direction and the connection will be interrupted.
What are the parameters of this switch?
The pole number of this switch is 2 because there are 2 separate switching subassemblies in it. These are independent from each other. You can connect up to 2 different circuits at the same time. The number of contacts is 1 because we can see only 1 contact for each subassembly.
This switch is only stable in 2 positions. That is, it is either off or on. It has no other positions. Are all switches like this?
No. The additional feature of the switches is the number of states they have, i.e. how many stable states the switch can be tilted into. This is not always 2. For example, there is a switch which has 1 pole and 2 contacts. However, it is a 3-state device because it has a certain stable state where it's connected to none of its contacts. For example, on hair dryers, it is common that when it is in the middle position, it's off. If you move it in one direction, it will only activate a slow speed, and if you move it in the other direction, it will activate a fast speed. This is typically a 3-position switch. You can see one of these 3-position switches in my hand. In the middle position, the pole does not come into electrical contact with any of the contacts. When I move this 3-position switch to this position, the middle outlet of the pole makes contact with this right contact. If I flip this switch to the left position, the same middle pole contacts the left contact, and the switch is again in the open position. In case of a device with m number of poles and n number of contacts, m number of poles can connect to n number of contacts. Separate abbreviations are used to indicate the internal design of the switches, which are the following. In this table, you can see the different abbreviations and their names and descriptions. The first 2 lines refer to the poles, the second or last 2 lines refer to the contacts. The abbreviation for single pole is SP, and there are double pole switches abbreviated to DP. Next, let's look at the designations for the contacts. The first one is single throw, abbreviated ST. The second one is double throw, abbreviated DT. These abbreviations have several different combinations in the market. SPST, SPDT, DPDT.
Tehát ugye single pole, single throw, single pole, double throw, double pole, double throw. Ezeket a jelöléseket fogom
I'll use these abbreviations below to simplify the illustration of the internal structures.
struktúrákat. A mechanikusan vezérelt
Another essential feature of the mechanically controlled switches is whether after the switchover, the switch remains in the position in which it is set or reverts back to the original position.
állapotba visszalép. A kapcsolóeszköz
Our two-contact switch device is bistable. After the switchover, the moving contact remains in the position where we have set it. Such typical devices can be seen in this figure, whose internal design was shown earlier before the three-position switches.
háromállású kapcsoló előtt. Bistabil működéses
Bistable operating devices can have 2, 3, or even more outputs too.
fajtája is. Az SPS
The SPST switch is a component with two outputs, which conducts current. In this case, it closes the circuit, or not. In this case, it breaks the circuit.
megszakítja az áramkört. Az
The SPDT, or three output devices, can be called toggles as well, because we can choose which output should be connected to the pole.
kivezetés legyen összekötve a pólussal. Az
Number 1 marks the pole, we call it common contactor as well.
a kettes
The numbers 2 and 3 mark the other two terminals. In the figure, you can see that practically the inside of the switches is only mechanically constructed.
And what about the rotary switches?
a forgókapcsoló
The rotary switch is a subtype of multiple output switches. Using our learned markings, these devices are single pole and contact components.
alkatrészek. Egy közös
We have a common pole which can be connected to n contacts.
erővel tudunk érintkezésbe hozni.
DPDT switches also belong to the group of multiple terminal switches.
Csoportjába tartozik.
The figure shows that this type of switch is like two SPDT, so single pole two terminal switches within one component.
És kapcsoló lenne egy alkatrészen belül.
Why is it good to have two switches in one physical component?
Because we can control and switch the two poles at the same time, meaning that we can switch two things independently from each other.
Egyetlen dolgot kapcsolgatni. Természetesen
Of course, there are such components which have several switches integrated into, i.e. several switches can be found inside a single component, and these are independent from each other. Such a device, as an example, is the DIP switch, which is none other than building multiple SPST switches into a single component.
Now I understand everything about the bistable switches. Can we talk about how the monostable switches work?
Those devices belong to the monostable group, which return to their original state after switchover.
lépnek vissza. Ennek az
The reason for this is if we stop pushing that button, i.e. the button has been released, then a small spring pushes back the contact to a stable state and it holds there as well.
ott is tartja.
In the figure, number 4 marks the spring, number 6 marks the push button of the device, number 3 marks the contact, which closes the two outputs 1 and 2 when the push button is pressed.
Ez az egyes és a kettes.
This is how a simple push button works. If it is pressed, then it conducts. After releasing it, it will become open again.
A fenti képeken példaként
The switches, shown by the figure above, are so-called normally open switches, abbreviated NO.
működésűek. Ez azt jelenti,
That means, in case of stable state, there is a break between the two outputs, so the circuit is open. If the push button conducts by default, and the circuit can be interrupted by pushing the button, then we're talking about a normally closed or NC switch.
normally closed NC kapcsolóról beszélünk. Itt láthattok a
Here you can see some buttons and switches on the table.
ezek elég
These are available in quite a variety of designs, some even have backlighting.
háttérvilágítása is van.
Here's one of them in my hand. Here's the little blue part that can light up on the push button.
Kék kis részt tud világítani a nyomógombon. Ilyen kapcsolódás.
You can see this type of push button in elevators, for example. On the back of it, you have to turn on the right voltage, and then this circular shape on the back of it lights up.
És akkor világítani kezd. Itt ez a kör alakú forma rajta. Itt az asztalon
There's also a light switch on the table. Now I want to show you how it works.
mutatni, ez
This is a normal light switch. You can find one at home.
ilyet otthon találtok.
We'll now test it with a multimeter. The multimeter is set to the continuity test position.
Használni. És a multimétert beállítjuk a folytonosságvizsgáló állásba. Ugye ez
The way it works is that if you touch two wires together, the multimeter beeps.
akkor sípol a multiméter. Most a multiméter
Now, I connect the wires of the multimeter to the corresponding outlets of the light switch,
kivezetése.
And if I switch the light switch, the multimeter beeps. This means that there is electrical contact between the contact and the pole.
So discussing this, we have reached the end of the mechanical switches.
Unfortunately, no. Unfortunately, nothing is ideal in reality, so we have to talk about a very important phenomenon, the bounce of the contacts. This can exist in any mechanical switch. For each mechanical switch, care must be taken to ensure that the contacts, when pressed together, first for a very short period of time with an imperceptibly small amplitude to the eye, can start bouncing on each other, and then the state of constant contact is set. This is what we call a bounce, which may cause some circuits to fail. I will illustrate the problem on this diagram with a push button. At the beginning of the picture, the button is not pressed, so there is no contact between the two contacts. At the moment marked with red, you press the button, which starts to flicker, so the contacts inside the button will come into contact for a little while, and then they won't come into contact again. This occurs several times until the final stable contact occurs between the two terminals, the status at the end of the figure. It's important to note that this action takes very little time, usually a few 10 milliseconds. This unwanted phenomenon will play a role in the rest of the curriculum, where we will build a protection against it. Now that we discussed this, we reach the end of mechanically controlled switches.
In the next chapter, we will talk about electronically controlled switches. See you in the next video. Bye!